Hi, I'm Professor Goins. In this video, I'm going to look at the convergence test called the root test. Okay, so for an infinite series, the sum over an, where an is greater than 0 for every positive integer, we could say greater than or equal to 0 for every positive integer, meaning that all the terms of the series are non-negative. Consider the following limit. I take the expression inside the summation, and I take the nth root of it. So square root of the second term, third root of the third term, fourth root of the fourth term, so on and so forth. And I take the limit of all of those. What happens in the particular case that limit was 2. Okay? So then I say that the limit as n goes to infinity, the nth root of those terms are 2. Then what can we say? All right. That means that the nth root of an is approximately 2 for large n. So once I get to, certainly the millionth term, maybe even the 12th term, the nth root of that value of an is approximately 2. Well, if I take both sides to the nth power, that means that an is approximately 2 to the n. So those terms are growing pretty quickly. In particular, they don't converge to 0. Hence, the series diverges by the divergence test. Remember, the divergence test says that the only way that a series, or one of the requirements for a series to converge, is that these terms must go to 0. That's not sufficient, but that is a requirement. Okay, so the root test. This is in the particular case that the limit at infinity of that expression is 2. Well, what about the other cases? So that's the context of the root test. This says that if all the terms are non-negative for every positive integer, so again, this just means all the terms are 0 or bigger, and I define rho to be the limit at infinity of the nth root of those terms, so the square root of the second, cube root of the third, so on and so forth. What can we say after we evaluate that limit? Well, in particular, what I just did over here, the rho value would be 2, and we found divergence. So rho only has to be bigger than 1. If rho is 1.1, it diverges. If rho is less than 1, the series converges. Bigger than 1, then it diverges. And if it equals 1, then it's inconclusive. That means that it could either converge or diverge. We just have to apply a different test. All right, let's look at the following series. Determine convergence or divergence of these 3 infinite series using the root test. All right. Part A. So the value of rho is the limit at infinity of the nth root of the expression inside the summation, being 2n plus 1 over 5n plus 1 to the nth power. Well, notice that the nth root and the nth power are going to cancel, leaving the limit at infinity of 2n plus 1 over 5n plus 1. And the limit at infinity of this expression here is 2/5. Okay. So then what does that tell me? Well, the value of rho is 2/5, and that's less than 1, therefore converges. Part B. Okay, we're going to take the limit at infinity of the nth root of the expression inside the summation, which is 1 minus 1 over n to the n squared. And when I take the nth root of the n squared power, remember this is the exponent 1 over n, so 1 over n times n squared leaves a factor of n, so this is the limit. N goes to infinity of 1 minus 1 over n to the n. And that limit should look familiar from earlier in your Calc 2 course, or even in your Calc 1 course. This is e to the power -1. Okay, so this would be e to the -1, which is 1 over e, and that's less than 1, because remember, e is bigger than 2, so therefore this series also converges. Part C. Rho is the limit at infinity of the nth root of the expression inside the summation, so that's n squared over 5 to the n. Okay, so the nth root of n squared is the nth root of n squared, and then the nth root of 5 to the n would be 5. And then, using continuity, the limit of the square is the square of the limits, meaning I can take the limit of nth root of n first and then square that. And the nth root of n is one of those common limits that you've learned in your section on sequences, which is 1. So that's 1 squared over 5, which is less than 1. Therefore, this series also converges. So all three of these series converge. Okay. Since all three of those converge, let's do another example. Yes, let's leave the statement of the root test up there. All right, so here's another example. Let's look at the following infinite series. The sum n equals 1 to infinity of 1 over n. So that's the geometric series that you should be familiar with, or most likely familiar with at this point in the Calc 2 course. So let's compute the value of rho. Rho is the limit as n goes to infinity, nth root 1 over n, which is the limit at infinity. Nth root of 1 is 1 over the nth root of n. So once again, I get this nth root of n limit, which we had over here. Of course, that's 1. And by the root test, it's inconclusive. Now, we have lots of ways that we can show that the geometric series is divergent. But the root test, and if you watch the video on the ratio test, both of those lead to inconclusive for the geometric series. If I were to get any value of rho that's bigger than 1, which is kind of the opening discussion that I had in this video, where rho is 2, then we know that it diverges. If I go back to, let's say, this previous example, so now this one is done, but all the work is here. So let's say I was to change this to make that a plus, and let's make that a 4. So make this 1 plus 4 over n to the n squared. What changes would we have in the solution? Well, this would be plus, that'd be 4. This would be plus, that'd be 4. Then make this e to the 4th, which would be bigger than 1, and therefore that one would diverge.